The earthquake that happened this morning, and I think it happened about 10 minutes before 8. Maybe the most important thing to say is that it was a moderate size earthquake.
Imagine this. It's early morning, February 24th, 1979. Most people in the tiny town of Randolph, Utah are still asleep. No alarm goes off, nobody feels anything, nobody hears a thing. And yet, at that exact moment, the earth shakes. Deep, incredibly deep. A seismograph at the University of Utah captures it, a magnitude 3.8 earthquake. Strong enough that people should have felt it, but nobody does. How is that possible? A young researcher leans over the data, and what he sees is so absurd, so impossible according to everything science knew at the time, that he can barely believe it himself. The earthquake didn't occur in the crust like they normally do. It occurred at a depth of 90 kilometers, deep inside Earth's mantle, a place where earthquakes simply should not exist. For almost 50 years, this finding was brushed aside, ignored, too crazy to take seriously, until now. Because in 2026, scientists at the University of Utah have definitively confirmed that earthquake was real, and it wasn't alone. Welcome. This is the story of the earthquake that shouldn't exist, and what its discovery means for everything we thought we knew about the ground beneath our feet. Part 1. What is an earthquake anyway? Before we go further, let's do a quick refresher, because to understand why this earthquake is so shocking, you need to know how earthquakes normally work. Earth is built like an onion. On the outside, you have the crust, the thin layer we live on. Continental crust averages about 30 to 50 kilometers thick. Oceanic crust is thinner, around 5 to 10 kilometers. Below that is the mantle, a massive layer of rock stretching from the base of the crust all the way down to about 2,900 kilometers. And then there's the core, but we'll leave that for another day. Now, earthquakes normally start in the crust. They begin at a fault line, a place where two pieces of rock slide past each other, collide, or pull apart. Enormous pressure and friction build up stress over time. At some point, the rock snaps. That snap is what we feel as an earthquake. This works because crustal rock is brittle. It can store stress and then suddenly release it. But in the mantle, the temperature there is so extreme, hundreds to thousands of degrees Celsius, that rock doesn't break, it flows. Incredibly slowly, over millions of years, but it flows. Like honey you warm up, it becomes liquid. And a flowing substance cannot cause an earthquake. That's not an opinion, that's physics. Or so we thought. Because that logic has one enormous problem: the 1979 earthquake in Utah. Part 2. The discovery nobody believed. Back to February 1979. George Zandt is a young postdoctoral researcher at the University of Utah. He works at the university's seismograph stations, and his job is to analyze earthquake data. On February 24th, the station detects an earthquake beneath Randolph, a tiny town in northeastern Utah, near the borders of Idaho and Wyoming. Magnitude 3.8. Nothing unusual, you'd think. At that strength, people should feel it. But two things immediately catch Zandt's attention. 1. Nobody felt the quake. Not a single report from locals, 0. 2. The seismic waves look strange. They have a pattern that doesn't match a normal crustal earthquake. So Zandt starts calculating. He analyzes the wave patterns, compares them to other earthquakes, and works out the depth from which the quake must have originated. And the answer he gets? 90 kilometers deep. He recalculates. Same answer. That's deeper than the bottom of the Earth's crust. That is, quite literally, inside the mantle. The deep depth explained why it wasn't felt by people at the surface, Zandt later said, but it was hard to convince others of the highly anomalous mantle earthquake occurring in a region where none should exist. He wrote a short note about his finding, an abstract for the journal Earthquake Notes, but it went largely unnoticed. Too controversial, too unbelievable. And just like that, George Zandt's discovery was buried in the archives for nearly half a century. Part 3. A new generation picks up the trail. Fast forward to the present. A new generation of seismologists at the same University of Utah starts re-examining archives data. They now have better tools, more powerful computers, and far more sophisticated analysis methods. Professor Keith Coper, a geology professor at the university, leads the team. They take the waveforms from the 1979 earthquake and put them through fresh analysis. But they also look at 8 other suspected deep earthquakes that had been recorded since then in northern Utah and southwestern Wyoming. And slowly, the picture begins to come into focus. One by one, they confirm it. All 9 earthquakes did not originate in the crust. They all happened well below the Moho, the official boundary between the crust and the mantle, named after Croatian geophysicist Andrija Mohorovičić, who first identified it in 1909. In this part of Utah, the Moho sits at around 45 to 50 kilometers depth. These earthquakes happened 5 to 60 kilometers below that boundary. The scientists published their findings in 2025 in the journal Geophysical Research Letters. But the story wasn't finished, because on September 10th, 2025, the Earth moved again. Part 4. The 2025 earthquake, the proof comes alive. September 10th, 2025, 6 o'clock in the evening, near the town of Mesa in Utah's Uinta Basin, the ground shakes. Magnitude 4.1. Again, almost nobody feels it. But the seismographs capture everything. And when Professor Coper's team analyzes the data, they find something extraordinary. This earthquake originated at 68 kilometers depth, more than 20 kilometers below the Moho. This was no longer a historical archive artifact. This was real-time confirmation that something fundamental is happening beneath Utah and Wyoming. Something we are only just beginning to understand. The team published this new case in April 2026 in The Seismic Record, under the title, The 10th of September 2025 Magnitude 4.1 Earthquake in Northeastern Utah, an archetypal continental mantle event. In other words, a textbook example of a continental mantle earthquake. Science now had a name for the phenomenon, CMEs, Continental Mantle Earthquakes. And with that, George Zandt's 1979 discovery was finally, after nearly 50 years, officially recognized. Part 5. Why here? The role of the Wyoming craton. Now the big question. Why is this happening here? Why Utah and Wyoming, and not everywhere else? The answer lies in a geological structure most people have never heard of, the Wyoming craton. A craton is an ancient, stable piece of continental lithosphere. It's literally the skeleton of a continent, billions of years old rock that barely changes. The Wyoming craton is one such structure, and it extends beneath a large portion of Wyoming and neighboring states. But here's the fascinating part. The western edge of the Wyoming craton borders the tectonically active western United States, a zone full of volcanoes, fault lines, and shifting tectonic plates. That's an unusual combination. An ancient, stable chunk of Earth sitting right next to an enormously dynamic zone.
Professor Coper explains it with a brilliant metaphor. Think of an iceberg in a river. On the scale of millions of years, the mantle is hitting the craton
and then flowing around it. It's that interaction, where mantle flow is being diverted around this hard cratonic route, that's causing the increased strain rate, the increased deformation, and it's also creating extra stresses. We think it's that interaction between the keel of the iceberg and the medium around it that's leading to these earthquakes. In other words, the Wyoming craton is like a boulder in the middle of a river. The water flows into it, around it, and through that turbulence, eddies and forces are created that wouldn't normally exist. In the Earth, that turbulence isn't water, but slowly flowing rock, and the forces it generates are apparently powerful enough to, against all expectations, cause that rock to break. There's also another mechanism researchers are investigating: thermal runaway. When rock is compressed under extreme pressure and heat, the friction can generate so much local warmth that the rock becomes even more fluid, which accelerates deformation, which generates more heat, until a fracture forms. This is a different kind of breaking than in the crust, but the result, an earthquake, is the same. Part 6. What does this mean for science? Okay, but why is this such a big deal? Aren't these just a handful of small earthquakes in a remote corner of America? Well, the implications reach far beyond Utah and Wyoming. First, we need to rewrite the textbooks. The definition of where earthquakes can occur has always been based on the assumption that mantle movements are too slow and too hot to cause brittle fractures. CMEs prove this isn't always true. There are conditions, specific geological structures, specific temperatures and pressures, under which mantle rock can still behave like a brittle material. That opens an entirely new field within seismology. Second, there are probably far more of these earthquakes than we realize. Because nobody took CMEs seriously, they were simply dismissed as measurement errors or data anomalies in the past. Now that scientists know what to look for, old archives are being re-examined. A global catalogue has already been published listing 459 confirmed continental mantle earthquakes since 1990, worldwide, not just in America. This phenomenon is not unique to Utah. It also occurs near the Himalayas and Tibet, and in other places where ancient cratons border active tectonic zones. Third, seismic hazard. This is the most practical question. Are these deep earthquakes dangerous? For now, the CMEs in Utah appear to have relatively small magnitudes, between 3.8 and 4.1. They aren't felt at the surface because of the enormous depth, but the discovery raises real questions. Can deeper mantle earthquakes reach larger magnitudes? And if they do, what are the consequences at the surface? Scientists don't know yet, but that's exactly why this research matters so much. Fourth, the nature of seismic silence. One of the most fascinating characteristics of CMEs is that they occur in isolation. They almost never have foreshocks or aftershocks. They shoot up from deep in the earth like lone wolves, and then it goes quiet again. That makes them exceptionally difficult to study. Normally, you use the aftershocks of an earthquake to map the fault zone. With CMEs, you don't have that. It's like a ghost briefly passing through a wall and then vanishing without a trace. Part 7. The man who was right all along. I want to take a moment to honor the man who started all of this, George Zandt. In 1979, he had the courage to say something that no colleague wanted to hear. He published his finding, watched it get ignored, and moved on with his career, eventually becoming a professor of geology at the University of Arizona. But the data stayed, and the questions stayed. Nearly 50 years later, the world has finally caught up. I did some other analysis that convinced me of the reality of the deep depth, Zandt said in a recent statement. But it was hard to convince others of the highly anomalous mantle earthquake occurring in a region where none should exist. That's a story that repeats itself throughout the history of science. An extraordinary discovery that arrives years, sometimes decades too early for the rest of the world to accept it. Sometimes the discoverer is right, sometimes they're not. But one thing always holds. Good data doesn't disappear. It waits. In George Zandt's case, it waited nearly 50 years.
Part 8. What comes next?
So what now? Professor Coper's team continues to monitor the region. They now know that more CMEs will likely follow. It's only a matter of time. With detection equipment far more advanced than what existed in 1979, these earthquakes can now be recorded and analysed in real time. There are also plans to expand the seismic network across the Wyoming craton area. More seismometers, more data, better maps of what is happening deep beneath the surface. Internationally, scientists are now re-examining earthquakes that were previously dismissed as anomalies. There may be more hidden CMEs waiting to be discovered in archives all around the world. And the big question remains, is this phenomenon rare, or does it happen far more often than we ever imagined? Earth has always guarded her secrets carefully, but with every new discovery like this one, we gain a little more insight into the enormous machine running beneath us, day and night, invisible and silent, until suddenly a seismograph needle spikes. The earthquake of February 24th, 1979, beneath Randolph, Utah, registered a magnitude of 3.8. Nobody felt it, nobody heard it. But somewhere in an archive cabinet at the University of Utah, it slept all those years, patiently waiting for the day science would finally take it seriously. That day has come, and what we now know fundamentally changes how we look at the Earth. Not just at what happens on the surface, but at what is truly taking place deep, deep below, in the hot, flowing interior of our planet. The Earth is far from finished speaking. If you found this video fascinating, hit that like button and subscribe to the channel. We regularly dive into the latest geological, astronomical, and scientific discoveries that will change the way you see the world. Until next time, take care of yourself and of the ground beneath your feet.